but we then give you an API in R, Python. We also have a web GUI, and anything you can use in Java, you can also use in Scala. So those are kind of the different ways that you can access H2O and use it. And one of the other things that's unique to H2O is that because the algorithms are written in Java, you can deploy models to production pretty easily as pure Java code. So if you have, an R package or a Python package, you would typically then deploy that into an R environment or a Python environment. There's newer things now where you could, probably pretty easily deploy an R model into a Python environment and vice versa. But the goal with this is to have very efficient models for when they're in production to make predictions quickly. So that's one of the goals. And then H2O has been around since about 2012. That's when the company H2O AI started, and it started just to create this platform. So at that time, Hadoop was the big data platform that everybody used. So originally, H2O was a platform, a machine learning library for Hadoop, and then Spark came along, and we basically rewrote everything actually to work with Spark. But those are just two ways that you can use it. So you don't have to use Hadoop or Spark to use H2O. Probably a majority of the people that use it just run it on their laptop, and it works basically as a replacement for any other machine learning library that you have. And it might just be a little bit faster and more parallelized than other ones that you use. Okay, so and here's just my one real technical slide. So I'm just going to introduce some terminology that we use in H2O, because there's probably these two things that you're not familiar with when you're new to H2O. So we have something that that we call the H2O cluster. And what that is it's just the name for where all the computation is happening. So that's where all the data lives. It's where all the machine learning happens. It's just the name of basically what the Java process in which everything happens. And if you run it on multiple nodes, it would be a shared Java process across, different machines. So the first thing that you do when you start up an H2O, well, when you start writing an H2O script in R, Python, or wherever, is you would start up the H2O cluster, and all that does is just create an environment for the compute to happen. And the way it works is you basically allocate a bunch of memory, and that's where everything happens. So if you need more memory, if your data is bigger, you just create a bigger cluster. So that's probably more than you actually need to know about that. So the next thing is what we call an H2O frame. And all that you really need to know about that is it's a data frame. And if you're in R, you would interact with it as if it were an R data frame. You can sort of do all the same things, like you subset the H2O frame the same way that you subset an R data frame. And then the same goes for Python, pandas data frames in Python. So if you already know how to do basic data operations in R or Python, you can do them on an H2O frame. And the only thing to note is underneath, if you're on a cluster, the way that it works is it's a distributed data frame where some of the rows are on one machine, the other rows are on another machine, and more other rows are on another machine. And basically that's how we do the distributed computing in H2O. And so when you're training a machine learning model, there's operations that are happening locally, and then the nodes communicate with the results and then make updates, and then it's sort of this iterative process. So yeah, I think that's probably all I need to say about that. And what you achieve by having a distributed data frame is that you can load let's say you work at some company and it's, you collect a lot of data. Let's say you have a 1 terabyte training set. It's pretty rare, but in theory, like you have a 1 terabyte training set. Well, you probably don't have a 1 terabyte machine or machine with a RAM of that big. And even if you do, you probably want a little bit more than that. So what you could do is you could go on Amazon EC2 and rent out collection of smaller machines, and then you can fit your data across those machines. So basically what you achieve is you're able to do machine learning on data sets that are bigger than what's typically common for like the RAM in a single instance or laptop or machine. Okay, so that's pretty technical. So we're going to move on to some other things. All right, so just a general overview about what's available in the H2O library. So it's basically just a collection of supervised and unsupervised machine learning algorithms. So probably a lot of the ones that you've heard of before: gradient boosting machines, random forest. We have some deep learning. We also have XGBoost, which is sort of a specific GBM that works really well. GLMs, we just added SVM. I think we're adding GAMs soon. So anyway, we have a lot of machine learning algorithms. So the goal here is just to make a unified interface to a bunch of machine learning algorithms that are scalable and distributed. And then we have everything that kind of goes around machine learning as well. So, and we try to make everything easy. So if there's something that you always have to do in a pipeline, like let's say for GLM, you always have to impute missing values if they're not there. So we do that stuff automatically. So anything that we can think of that makes sense to sort of do automatically and for you, we try to do that. So let's see, that also involves handling categorical columns automatically, so you don't have to do anything to your data before handing it over to the machine learning algorithm. If you have categorical data, we'll handle that for you. And then there's some other, sort of more advanced features, like on some of the algorithms, like for example, GBMs, gradient boosting machines, they can overfit if you train them too long. So we have mechanisms for doing early stopping automatically in a GBM, for example. So we have little built-in things that we try to help you get good performance and to help you simplify the data science process. Some other things, we have cross-validation, grid search, random search. We have different types of encoding techniques, something called target encoding, which is quite popular on places like Kaggle. And then once you have the models, we can give you variable importance for any model, and then model evaluation metrics like mean squared error, AUC, et cetera, and then plots as well. So we try to make everything included so that you don't need to piece together other libraries that you're, to do the whole thing. So, all right. Okay, so let's move on to Auto ML. So, all right, so this is my slide where I'll kind of at least give my opinion about this. So what I think are the goals, some of the goals of Auto ML, and then some of the features of Auto ML as well. So I think like probably the simplest definition of Auto ML is, well, I guess you should say, I'll say train the best model in the least amount of time, but I guess I should also add the caveat without any tuning or any manual intervention, basically. So the goal would be having like one line of code that says, Auto ML, and then you give it your data set and you specify a time limit and you hope to get the best model possible within that time. So I think that's kind of the goal, in my opinion. You could have other goals that are sort of adjacent to that, where you could say, give me the best interpretable model in the least amount of time, or you could put other constraints. or just, the best tree-based model in the least amount of time. There could be subsets of that where people could also call that AutoML. And I think also one of the goals is to just reduce the effort and that it takes to train a model, and that could just be number of lines of code that's required to write to train a model would be reduced, or I guess the amount of thinking that goes into it beforehand, like choosing an algorithm, choosing hyperparameters, etc. And then also we want to reduce the expertise required, and those kind of go hand in hand. But it's a lot of work as a data scientist to know every single algorithm and all the important hyperparameters and all the ranges for the hyperparameters that make sense, and knowing when to use which algorithm, when to combine algorithms together, how to pre-process the data. It's, after many, many years of being a data scientist, this stuff, but it's really takes a long time and a lot of experience to do it. And, if you're the type of data scientist who maybe is some sort of consultant and has a lot of exposure to a lot of different data sets and a lot of problems, maybe you'll learn it more quickly. But sometimes people, they work as a data scientist at a particular company and they have, only, let's say, 2 or 3 data sets that they ever work on. And, you're not going to gain that experience quickly, even if you're working in industry for 3 to 5 years. If you're kind of only looking at certain things, it's useful. But then if you switch to a new job and the data's very different, you have to start over. So anyway, so AutoML is really, it's for everybody. It's not just for people who, don't know machine learning and need a tool to help. It's for people who want to be efficient with their time, want to train more models, want to learn more about machine learning. Because I also consider it to be a learning tool, because when something's done automatically and you get to see the results, you learn from that and you see things that you wouldn't have tried on your own. So there's really a lot of benefits to AutoML, in my opinion. And then, one of the features of AutoML is generally you get better models than you would tuning by yourself. Now, if you're an expert data scientist, that might not be the case. Maybe you start with AutoML, see what's happening there, you look at what the best models are, and then maybe you can take those and then do more manual tweaking and actually get a better model. But I think for the most part, at least given the time frame, you get much better results quickly. And then another thing I think that maybe is, not something people think about right away, but I think is also quite valuable, is that it increases reproducibility. Across an organization, if you have 20 different data scientists, you might, have a problem and you get 20 different solutions. And maybe there's one that's the best if you measure model performance, but, generally people have more comfort with certain algorithms that they are used to using, and other people have different comfort zones. So, if you're a boss and you're handing off a problem to a data scientist, you might get different results depending on who you hand it to. So I think one nice thing is that when you run an AutoML algorithm, you can still go off and do whatever creative process you have as a data scientist. But when you run an AutoML algorithm, you have a baseline that you can compare everything against, and everyone could, run that, and then, you always get the same result, and it just creates like a nice benchmark across an organization, but also just for a data scientist, as like, run it first on AutoML and then see if you can do better, and that establishes like a lower bound for what you can do. And then I'll just say, yeah, for scientific research, especially, like, I read a lot of papers about applied machine learning, and it's some interesting problem, like, they're trying to do some diagnostic in medicine or something like that. And they just, they picked a random forest and they used, maybe tuned the M-try a little bit, but then, they probably could have done better if they had just an Auto ML tool. So, you don't, when you're applying machine learning into some field, you always want to use like the best tool available, because you want to know like what is really possible in this problem that I'm trying to solve. And so if you just use a random forest and then put that in your paper, people will know how that's done on a random forest, but they won't know like, could this have been much better? So I think if, researchers could always kind of benchmark against a, common Auto ML tool, it would be more informative. That's just my opinion, but okay. So here's kind of just the aspects of, this is, I would say, aspects of machine learning in general, or data science in general. So when you're building models, you have to do some sort of, usually some sort of data preparation, and I'll go into more details on the next slide about each of these. But then once the data is, ready to go for the machine learning algorithms, you're going to have to probably generate quite a few models. You typically don't know what the best model should be without trying a whole bunch of things. So, there's a phase where you're generating a lot of models. And then this is maybe an optional thing at the end, but it's something that I always do, or I always like to do, is doing some sort of ensembling of the models. Because if your goal is to get the best model, generally that means you're ensembling something. And you might have a different goal. Your goal might be, I just want a single model, and then you choose the best from, the second phase there, and you don't do an ensemble. But so that's kind of up to the person doing it. Okay, so here's just a little bit more info about these steps. So by data preprocess, I mean anything that relates to like different types of encodings of categoricals, or imputation, or standardization. That could include feature selection, feature extraction. It's pretty self-explanatory, but anything where you're processing the data just in a very basic sense, or if you're actually creating new features, or deleting features, or editing the feature space in some way. And then for model generation, there's lots of different ways that we can generate models. So probably the most common or straightforward would be grid search, or random search. And then another one that's popular is called Bayesian hyperparameter optimization. So that's more of like, you're generating a lot of models, but so you could think about it as model generation, but you can also think about it as tuning. And there's a number of other techniques. Those are just kind of the two main ones. There's, in the last couple years, some interesting new techniques. One's called hyperband. One takes hyperband and Bayesian hyperparameter optimization and combines them together. That's called BOHB, B-O-H-B. So there's all different new techniques in AutoML. And then for ensembles, there's a bunch of different ways to do that. The most common way, I think, is called stacking. Sometimes it's also called superlearning. It's the same thing. That's a technique of using machine learning to learn what the best combination of the models is. So it's like a secondary set of machine learning that happens. And then ensemble selection is a little bit different, where you either start with all the models and successively delete ones, or vice versa, where you start with no models and you add them in, and you do that in a greedy way such that you basically stop doing it when it starts to hurt the performance. Okay, so the term AutoML, that's been around for a while. But there are starting to be more tools that are called something AutoML. So like H2O Auto ML, Google Auto ML, etc. So just to be clear, AutoML is let's say a noun, not a proper noun. It's not the name of a tool, it's a technique or a field in itself. So, and there's lots of different types of AutoML as well. So what I'm talking about today is primarily AutoML related to tabular data. and supervised learning. So, and that's just sort of one subset of AutoML. Then there's a whole nother field just basically related to deep learning. So deep learning AutoML techniques are very different than, other techniques. So if you have like image data or text data or something like this, so that's not tabular data. So it's pretty much the type of your data determines what kind of algorithms you're going to want to use and then what type of AutoML. So anyway, if you want to learn more about all the different types, there's a blog post that I wrote that's called The Different Flavors of AutoML. And there's a link to it there. And yeah, I go over a number of different techniques and software packages and just kind of gives a broad overview of AutoML, because sometimes I see articles and people are only talking about deep learning and it's like as if they don't know that all the other stuff exists, or vice versa. So it's important to recognize that when we use a term in a generic way, we want to make sure that it's inclusive of everything, or at least be aware that there's other stuff out there. Okay, so for H2O Auto ML, so this is these are the things that we have in the current version. So for all H2O algorithms, we do imputation, one-hot encoding, and standardization automatically. So that's something we just get for free because we're using H2O. So in the next version of H2O, so there's something called target encoding, which is quite useful for if you have high cardinality categorical features. So let's say you have something like a zip code in your data set. So zip code, there's like, 40 some thousand possible zip codes. So in that one column, you could have 40,000 different categories. So that's generally highly problematic to machine learning software. So you usually have to do something with that column to make it so that it doesn't completely break your software. So there's different types of encoding techniques, and one of them is called target encoding, and we've recently added that to H2O. So now that it's in H2O, we can add it to AutoML, and we can handle these high cardinality categorical features automatically. So that's not in the current version, but that's something that we're working on right now. And then the other two things you see sort of grayed out right now are feature selection and feature extraction, and those are all stuff that's on our roadmap as well. For model generation, what we do is something, a combination of random grid search and stacking. So I won't say, let's see, I think on the next slide I might have some information about that. Yeah. So why do we do this? So one reason is that, well, in H2O, we have grid search, and then we have something called random grid search, which is just randomly selecting from a grid and then training models. And the reason that these two things work well together is because for stacked ensembles do well if they have diverse collections of models together. So one way to get a diverse set of models to do stacking with is to randomly generate them. And so that's why we combine random grid search with stacking, is because we're getting something kind of random, and then that helps the ensemble learn. So basically ensembles perform well if the individual models are strong, but maybe they fail in different ways. So maybe you have a deep learning model and a random forest, and those probably fail in different ways, so they're good if you combine them together. I think I have some slides about stacking, but I'm gonna skip that due to time, and it's probably a bit too technical, but it's here for reference for later if you want to understand how the stacking algorithm works, because it's actually quite simple and you could probably implement it yourself. So I'm going to skip that. Okay, so this is just a little overview of what I mentioned so far in H2O Auto ML. So we have the basic data pre-processing. We're training a random grid of a bunch of algorithms. So part of the contribution that we've made to AutoML is we've consulted within H2O a lot of expert data scientists and kind of come to an agreement about what we think is reasonable for, like if we want to have a grid search for GBM, like what do we think is a good set of hyperparameters to look at, and what are the ranges that we want to look at. So that in itself is a little bit hard to define, and it's also something that we are constantly benchmarking and tweaking over time. So the algorithm that we've created is something that's evolving over time. It's not just we created it once and it's going to stay the same. So that's kind of one of the things about AutoML. There's no definition of what it is. It's just a set of goals. And so we're always trying to achieve better convergence on those goals. So we're always trying to improve the algorithm. So if that means that we find that, maybe the learning rate range that we gave our GBMs is not good enough, maybe we need to change it a little bit, then we'll do that in the next version. So we've, defined these grids for all the algorithms, and then we tune all the models using cross-validation so that they don't overfit. And then at the end, we train 2 different stacked ensembles. So one of them is using all the models that we've trained during the process. And then another one, so that might be, let's say you train it for 5 hours and you get 100 models. You have 100 model ensemble. So it might be the best model, but you might not really want to put 100 model ensemble into production. Maybe you don't need that last little bit of performance. So maybe you could do like a little bit more simplified version of that. So we have another ensemble that just takes the best from each category of algorithm. So best GBM, best deep neural network, best GLM, best random forest, best XGBoost model, and then makes an ensemble from those. And that's usually the second best model at the end. The biggest, the big stacked ensemble is usually the best, then this one is the second, and then typically we see an XGBoost model as like the best single model, but that's not always the case. And then what you get back from this AutoML function is an object that has something that we call the leaderboard, and I'll show you an example of what that is. That's where we give you scores for all the models that you trained during the process, and we rank them. And then, of course, because this is H2O and we're just training H2O models, everything remains the same about productionizing models. So then we have a bunch of H2O models that can be easily productionized. So let me just show you quickly what the code would look like. So here's what it looks like in Python. So I mentioned at the beginning of the talk, the H2O.init, that's where we're just starting the H2O cluster. So every script will have that at the top. And then we need some data, so we import some data. In this case, I'm just showing the most simple example. Let's just load it from a CSV file. And then we have 2 lines of code here, because this is generally a more Pythonic way of doing machine learning. So first we create an object of type H2O Auto ML, and we put any kind of parameters to describe that in there. So this, we're going to control the time. So we're going to say I want to run for 600 seconds, which is 10 minutes. So I'm saying I want to run AutoML for 10 minutes. And then we're going to execute the .train method. And then at that point, we tell it what data we want it to run on. So the data that we gave is the training frame that we just imported. And then the only other thing it needs to know is which of the columns is the response column or the outcome. If there's other columns in your data that you want to ignore, let's say you have an ID column or some date column that you don't need, you can also pass along an X argument, which specifies the specific predictor columns that you want to use. So otherwise, it will just assume everything that's not the response. Those are features, use those to train. And then once you're done training, you get this leaderboard back. And then let me show you next, just in R. Same thing, just one line of code this time instead of two. So we start up the H2O cluster, import the data, and then we've got H2O.AutoML function, and all the arguments go in there. And I have only a few minutes left, so I'm just going to show you. Let me just show you how we do this in our web GUI. It's basically the same thing. And every time you start up an H2O cluster, it starts a web server. And then this thing is running in your browser, basically. If you type in the URL or the IP and port where this is running, you'll get this little GUI that pops up, and you can do everything that we've just talked about without writing any code. And then this is just what a leaderboard looks like. So in the model ID section, you just have a bunch of models, and they have names which indicate what type of model they are. But then, it doesn't say anything about the hyperparameters or anything like that. So if you want to look and see more about that model, you just grab the model by model ID. There's a function called getModel, and you just get model and pass in the model ID, and then you can inspect the model more closely. And I only have a few minutes left, so let me just see if there's anything else. I'm going to skip this. This is here just for later. It's just giving some tips. You can turn on and off certain algorithms if you know that you don't want them to be used. The default runtime is 1 hour, so that's just to make sure people don't start running code forever without it ever stopping. So it'll stop after 1 hour unless you change the max runtime seconds. And let's see. I'm going to skip over this, and I'm just going to go right to the end. One more thing I'll say is you might not know, so I mentioned that you could train the AutoML process by the time limit. So you can also train it by the number of models. So if you don't, let's say that's a better way for you to think about what you're working on, you could just say, run this for 20 models and then, stop, basically. So one method you might do is you might say, I just want to see where I'm at, so I'm just going to, run it for 10 or 20 models and see where I get to, and then check the results. And then I want to continue to run it. So there's a way to do that. You just have to use this argument called project name, and then make sure that you set it the same each time. And then you can train 20 models, and if it's, maybe you're satisfied but you think it can do better, train for another 20 models, etc. Here's our roadmap. I won't go into details just due to time, but we're always open to user input, and that's how we decide what our roadmap is. So if you're using the tool and there's something missing, or you have an idea, or like something that you want to tell us, you can just get in touch, and my email will be at the end of the slide. If you're curious about how H2O AutoML compares to other open source AutoML tools, I, along with a bunch of AutoML researchers, we wrote a benchmark, or we performed a benchmark. So there's a paper there if you're interested. It's comparing against, there's not that many tools. So there's Teapot, there's AutoSKLearn. Both of those are on top of scikit-learn. And then there's another one called AutoWeka. And there are a few others, but those are kind of the main ones that we looked at, and the main ones that people use. And then this is some URLs that you can look and actually have more code to do the tutorials, more resources, and then my contact information. So I'll stop there. And then I guess we'll go to questions. And
yeah, okay. Thank you, Dr. Liddell. That was very fantastic talk, very interesting. Thank you. It seems that we have probably 10 to 15 minutes for wrap up and questions. And in order to avoid chaos, I would ask everybody in the meeting to type your questions in the chat box instead of unmute, so that it would be easier, and I will go through all the questions in temporal order, perhaps. And while everybody's typing, I actually have a question for you, Dr. Liddell.
sure.
Yeah, so it is my understanding that some of the machine learning algorithms, so it's more easily for them to be implemented as scalable, but others has more challenges. Like I heard that support vector machines could have some scalability challenges. So what's the difference between these two kinds of algorithms? Is there an easy way to tell between the two? And would you give some examples? Yeah.
Yeah, good question. So I might have been the one that said something about SVM not being scalable. Some heard me say that before, which is interesting because we did just add SVM to H2O, but we hadn't added it for, since the beginning of H2O, which is 7 years. Because of scalability reasons, it's just not an algorithm that is easily scalable. And that's just, I don't know if there's a way to describe why, but basically just the way certain algorithms work, they don't scale well. And SVM is one of them. But, during the last, let's say 10 years, one of the things that researchers like to do is take algorithms and try to make them scalable. So there's different techniques where you can kind of like cut corners on certain approximations and do certain things that you get pretty much the same results, but you've done things like, rather than loading the whole data frame into memory and doing some sort of inverse matrix operation on the whole data frame, maybe you've split it up into littler pieces and you can take inverse on smaller things. There's all sorts of like computational techniques that can be used. And I'm not super familiar with how we what the technique that we used to make our SVM scalable, but there is a paper about it that was, I think it was just called the parallel SVM. And so what we do is we'll look at a paper and then we'll just implement what's in the paper, and we'll try to do it, with high engineering integrity and try to do a really good job or a really good implementation. Because a lot of times a research paper is done, by a grad student or postdoc or somebody in academia, and they do it just to prove it can be done. And that, the goal isn't necessarily the best engineering ever. So they do it, show it can be done, and then we try to take that to the next level. And so, yeah, there's some algorithms as well that are very hard to parallelize, like the GBM is a complicated one. So I think there's a lot of tricks that go into that, like pre-calculating histograms and sending them around to all the nodes and things like that, where we can make sure the data is all where it needs to be at the time that we need it, so that it's not a matter of copying data back and forth. So there's all different techniques. And probably the best way to find out if an algorithm is scalable is just to Google, is such and such algorithm scalable, and somebody will have written a paper about it, or one way or the other.
Okay, thank you. We seem to have a lot of questions in chat box now, and let's go from one by one. So the first question we have is, how is H2O Auto ML compared to the other Auto ML platforms?
Oh, well, that's a good question. So we also were wondering that, and that's why we did this benchmark. So I guess so. Yeah, there's proprietary AutoML platforms, and then there's open source. So for the most part, like I have a pretty good understanding of how we compare to the open source tools. And I would say that it's hard. So part of what about benchmarking, which is difficult, is there's so many subsets of domains that you have to look at. So you have to look at very wide data. You have to look at data sets that have a lot of missing values, a lot of high cardinality, a lot of weird issues like extreme class imbalance. So we try to come up with a big collection of data sets that are representative of a lot of different weird problems that you might see in the real world. And then we ran the benchmark on all of them, and you can see that like on certain types of data sets or certain sizes of data sets that different tools perform differently, you know. So for Teapot and Auto sklearn, those are both libraries written on top of scikit-learn. So no matter what the technique that they're using is, there's some inherent scalability issues because scikit-learn isn't necessarily the most scalable library. So on smaller data sets, those do better than on bigger data sets. So it depends on what kind of data you have. And then once you kind of identify the data type, then you can narrow down and look at and see, okay, for this type of data, was there any difference between the tools? And so we try to explore or give people the ability to explore that in the benchmark itself, because it's really like hard and inappropriate to say one tool is always better. The one kind of conclusion that we put in the paper was that AutoWeka is worse than all the tools, like by far. So that's a much older tool. It was probably one of the first AutoML tools. So it just doesn't really do well at all. And you'll see that in the benchmarks. But for small data sets, Teapot, Auto sklearn, and H2O Auto ML are similar. I think I would say that looking at the results, the H2O Auto ML results are slightly better. But, and then we only looked at data sets of less than like 100,000 rows. So once you have bigger data sets, then H2O is going to excel more because it can handle the scalability issues. And in terms of like proprietary tools, we're also looking to do benchmarks on that, but it's obviously more difficult because you have to get access to those tools. Some of them are cloud-based, so like Google AutoML, I could get access, I just have to pay for it. But then other ones, you have to buy a license, and those companies won't sell me a license because I'm a competitor. So I can't benchmark them. But yeah, I think you'll see a lot more benchmarking stuff going on since there's a lot more companies involved now rather than just researchers. So then the stakes are higher and it's more important to get truthful information out there about how they compare. So one of my goals is to keep working on these benchmarks.
Okay, sounds great. And I think I see a couple questions which, in my opinion, actually belong to the same category. Is about how flexible the AutoML is. I see some questions related to whether it deals with non-continuous response outcome, and also whether you can add customized models, or how it deals with missing value issues. And specifically also we have other audiences asking about whether you can customize feature selection. So basically I feel like it's related to how AutoML is able to deal with the flexible process of building machine learning models, because you also mentioned, as you also mentioned in your talk, that this is a very interactive process and you do sometimes need to tweak the data and understand the data to do that. So would you kind of comment on those general questions together as, yeah.
Yeah. Okay, so the first one was does it deal with a non-continuous response?
Yeah.
I'm not sure, it does regression, multi-class classification, and binary classification. So I'm not sure exactly if that's answering the question. I'm not sure what they mean by non-continuous, because I think that just would mean classification.
Yeah, I think so.
Okay. Yeah, so the answer would be yes, we do. We do all the normal tasks for supervised learning. Um, and let's see, around pre-processing. So some of the stuff that we're adding, so we don't have a lot of, like, for example, there's not automatic feature engineering inside of H2O Auto ML. And we are adding some stuff to deal with the categorical column. So I mentioned we're adding target encoding. So when you have these problematic columns in your data, we'll see them and then we'll do something to transform the data automatically. And that's just, it's happening, but it's not in the current release yet. And then there'll be other stuff that we're going to add as well, which I mentioned, like feature selection, feature extraction, basically just, you know, anything that we can think of to automate the feature engineering in an automated way. A lot of feature engineering is hard to anticipate in advance, or, you know, maybe you take other data sources and bring them in and merge stuff. So whatever we can think of that could be automated, you know, we're adding that in. We also, H2O also has another AutoML tool that's called Driverless AI, which is our closed source AutoML tool, which is a completely different code base than this, and it's run on GPUs, and there's a whole bunch of other differences, but one of the features of that tool is, one of the prominent features of that tool is automatic feature engineering. So if that's something that you're interested in, there's more information about that on the website. But yeah, we're also adding, you know, our goal is to be, you know, the best or one of the best open source AutoML tools. And if other tools are doing things with feature engineering, we're going to have to do that as well, just to compete. So whatever we can think of to add, we will. And then around customized models, that was actually something that an H2O enterprise support customer asked us for recently, so we're adding it. So essentially one of the, you know, at H2O, we're a business, so we have open source software. So one of the ways that we make money is we offer enterprise support for our tool. So, so what we have is we have a lot of good feedback from our customers that say, oh, I need, you know, I need you to add this thing, and then we add it basically. So recently somebody requested that, so that's going in, I think, in the next version as well. So what that will look like is you probably pass in like a dictionary that defines the models, you know, like it will have algorithm name and then any kind of hyperparameters that you want. Probably we should make it so that you can also pass in a grid instead of just a single model. And then you could also turn off parts of our AutoML if you want to overwrite that or blend it in some way. And then your models would go into the leaderboard. They would also get included into the Stack Ensemble, and so it'd be just yeah, another interface. Let's see. So I think those are the three that kind of relate to customization.
Yeah.
Yeah.
Okay.
And I
Thank
see
you.
the one below about missing data. I'll just answer quickly. So for the tree-based algorithms, we don't need to impute anything. We just send those NAs down the tree, and they get put randomly in a bin. So we don't have to do any imputation for trees. And for the other algorithms, the default is that we'll impute the mean or the mode if it's categorical. But you can change that, or you can do your own imputation before you give it over to H2O machine learning algorithm. We have some different options for that.
Okay, sounds great. Thank you for the answers. And I think we are just ran out of time. And so I think we just need to stop here, and we will put the slides and the video, and which contains many of the resources for H2O on our website. Due to the time, we apologize that we couldn't get to all the questions. So if you have additional questions, please reach out to the speaker and to us through our online or WeChat platforms. And let's all thank our speaker today, Dr. Liddell, for her great talk again. And thank you all for joining our webinar, and we hope you have a wonderful day.
Thank you.